So instantaneous rates of change, I said that faster than I we're going to use some intervals to solve it. So they've given us our function here. F at x is equal to blah. We have a bunch of numbers and a root function. And we want to calculate the instantaneous rate of change at about approximately 4. Okay. Rate of change is slope, which is something you actually learn in grade 9. They usually use triangles to represent slope. So your slope is the change in y over the change in x. So in grade 9, they usually teach you that too as y2 subtract y1 divided by x2 subtract x1. Okay? But we don't really use y anymore. We use f at x.
Right.
So think of it like you're looking at f at x of your first term, or f at x2 over x2. Whoops, that's not an x, that's a giant 2. Okay. Subtracted by f at x1, that's your y1, subtract x1. So the idea, or the x's are still the same, whatever value we're plugging in, those stay the same. But instead of using y's, we use the function f at x instead. And these two refer to the same coordinates, while these two refer to the same coordinates along whatever the function is. We usually use this for something that's linear, but we're going to use this for any type of function. It could be a parabola, we could have like a cubic function, but the rate of change is always the slope, so you're looking for a slope along that line. Instantaneous is an idea of something that is tangent, so say I have this little parabola. I want to find the instantaneous rate of change at 4. I'm looking for the linear line that just touches that and goes away. Okay, we're looking for something that's tangent there. So we're going to use intervals to solve this. Because we're looking with the value of 4, okay, we're going to kind of split 4 using a number line here. So the idea is, 4 is our value in the middle. We're looking for the instantaneous rate of change there. We could take a value of something like 5. Whoops, 5 doesn't end up there. 3 does. 5 would be on the other side. We have 3, and this would be 5. Okay. So for our intervals, I could choose 3 and 4, but they're actually pretty far apart when you get down to like small values, right? And I could use 4 and 5, but again, there's a lot of numbers in between that. In fact, there's actually an infinite number of numbers. So, we could use 3.5 and 4.5, but we know, because we've worked with math so much, we can get much closer. So we might want to work with something like 3.9. We'd say repeated, but I can't calculate that by hand, so maybe 999 to 3 decimal places. And something like 4.001. Those are far closer to 4, which means they'd be much closer to being instantaneous. If I were to use like 3 and 4, again, I'll kind of show you using that parabola idea. If we say this is where 4 is, and this is where 3 is, well, then I'm looking at a line that does that, and that's kind of cutting through the whole parabola. That's not really instantaneous. And if we use the value of 5, I should have used a much better value here, but look at how different our slope is, okay? Right. So those are two very different slopes, when really instantaneous rate of change is one slope, and it's tangent like that. Okay, so that's why we want to get as close as possible when we set it up. So we got our function here. Okay, so we're going to use our function. We're going to use, when f at x is 4, we're going to use the actual value of 4. Okay, so when f is 4, and we want to calculate when f is 3.999. So we're going to plug those in and get actual values. So let's get 5, 3, 4.
So would this be for preceding?
Yes, this would be preceding the value.
So this is a number before and after.
Yeah, usually what they say is this is when we're approaching x from the left. They usually use an arrow notation. When x approaches from the left, that's not the notation. Shoot, I don't remember it off the top of my head. I'm going to look in a book and show you in a second. Right. But it would be an arrow coming from the left side, and then as x approaches it from the right side. Those aren't the notations. Don't strike it as me, but that's the idea. One coming from the left, one coming from the right. So we replace the x in here with the value of 4, and we replace the x in this equation with the value of 3.999, subtract 1. then plus 2 outside of the brackets. So we actually calculate all of this before we put it into our slope formula.
Mhm.
So we go about doing that. Here's our 3, 9. It replaces our x. Let's see if I can do this quickly. Oh, I wish I used a nice number. 3. Oh, I did, actually. This will work out nice. This is going to become 3 times 3, which is 9.
Yeah.
Root of 9 is 3. So we're looking at 5 times 3 plus 2, which should be 17.
Yeah.
Excellent. Now this one won't be so nice, so we'll use a calculator to calculate this one. It's going to be 2.99.
And then times 3.
So does that become 2.99 like this?
Yeah.
Pretty much. Times 5 plus 2.
Isn't there a 3 on the outside of it?
Yeah, I was thinking of after it's rooted. Let's see how close I was. 2.999 times 3 equals, and then if I want the square root, where's my square root of the above answer? 2.9994. Yeah, okay. Oh, I can't believe
Plus
it.
the 2 is 4.999.
So times 5 plus 2.
Oh, maybe I got mine wrong.
Yeah. That was the root, 2.99. Then we had to still multiply by 5
okay.
and then add the 2.
I forgot that.
That's okay. So 16.99, we'll say. So again, really, really close to 17, but technically not quite the number. And I did some rounding, which I shouldn't. I should really try to write this all the way out. I'm just trying for simplicity's sake here.
Yeah.
Okay. So now this is your kind of like your y2 and your y1. You have your coordinates. We've plugged them in. This is technically a coordinate. At 4, we're at 17. And at 3.999, repeat it, we're at 16 point, let's go to at least 3 decimal places. 997, okay. 997. So now we use these coordinates. You can think of them as your x1 and y1 and x2 and y2, but they'll usually show you as a function notation. We put them into our slope. So we can say that 16.997 subtract 17. This is our change in y over our change in x divided by, what was it, 3.99? 3.999 subtract 4. So let's see what we get here. Use our calculator. This is going to be 0.003. Is that right? Negative?
Yeah.
And negative 0.001, which should become positive 3. I'm going to double check. Sometimes I just say things. And I'm not sure. Okay, that would be 3, but let's make sure my other math is right.
Yeah, 3.
Yeah, 3? Excellent. You say it, you got it. Okay, so what we're saying is as we're approaching from the left, the instantaneous rate of change is 3. To do it from the right, we do the exact same process.
So
but
the right would be following?
Yes, it'd be following. And you would use like 4.001, and we'd run through the exact same process and find out. So if you got a value that was approximately 3 again, then you can kind of make the assumption that at 4, the instantaneous rate of change is going to be 3.
He said that like average is the center. So like